lecture we are going to discuss about experimental physics of interfacing lab, which is basically performed using an expEYES kit. So in this lecture we are going to study about the circuit response when it is constructed as an integrator and a differentiator. Now this particular experiment has three parts: construction of an integrator circuit, a differentiator circuit, and analysis of signals, Fourier analysis of signals through Fourier transform. So this aim of this experiment has two parts. First part is study of RC as an integrator and RC as a differentiator. Any low pass RC circuit acts as an integrator and high pass RC circuit acts as a differentiator. So integrator and differentiator circuits can be constructed either using RL or using RC, or it can be constructed using integrated chips also like PAMP and some other complicated elements. In this particular experiment we choose the simple element RC, resistor and capacitor connected in series. The second part of the experiment is actually to study and analyze Fourier transform of sine and square wave signals. Let us start with the differentiator circuit, RC differentiator circuit. So the circuit connections are like this. Q1, A1, A2 are actually the terminals from the expEYES kit. SQ1 is a square wave generator, A1, A2 are input signal to measure the signals. A1 measures input signals, A2 measures output signals across resistance. So this is basically a high pass filter, acts as a differentiator. To understand the circuit behavior, one has to design the circuit and then we have to analyze how the circuit performs. For that, let us choose the time constant of the circuit, RC circuit, which is nothing but simply the product of R and C is the time constant of RC circuit. So that can be chosen while designing a value lying between 1 millisecond to 5 millisecond. This limitation is only due to the limitations of the expEYES kit. In fact, it can go up to 50 milliseconds in the new expEYES kit, expEYES 17. The corresponding up frequency, if tau is chosen, will be reciprocal of the tau is the corresponding frequency of the circuit. So that will be in kilohertz because the time is in millisecond. Then choose one capacitor, let it be 1 microfarad. Estimate the value of resistance needed to be constructed a differentiator circuit for the designed F value. Okay, so that completes the designing part of the circuit. Then for the sake of avoiding distortion in the output signal, always avoid using capacitor more than 10 microfarad. If you use capacitor more than 10 microfarad, then resistance should be more than 2 kilo ohm. So that imposes certain conditions in the designing. The procedure is to construct the circuit, then apply the set frequency as that of the desired frequency. So applied frequency, I am calling it as F prime, the design frequency as F. So in the first case, F prime is applied equal to F prime equals S. Then the output signal and input signal are measured directly on the monitor on the GUI of the expEYES kit. For that, you connect A1, A2 and check their boxes to get the values of frequencies, voltages, etc. of the signals. Measure input and output peak voltages for the signal of this differentiator circuit. Okay, repeat this experiment for 4 more applied frequencies. Say this is thumb rule, F prime applied frequency to be equal to 1/100th of the design frequency F. Second one is 1/10th of the design frequency. Third one is 10 times the design frequency, and fourth one is 100 times the design frequency. Totally, so one has to perform 5 different values. Experiment one has to 5 different values, and one has to observe how actually the circuit behaves for these 5 different values of applied frequencies. So there is some restriction that actually the expEYES kit generates signals from say 5 Hz to 10 kilohertz. The experimental output may be somewhat limited, more limited. It can work up to only about 5 kilohertz. So keeping that, one has to design the value of one has to design the circuit with a time and frequency value lying between that, and also allowing all these 5 tiles. So if you design some extreme value, you may not be succeeding performing all these 5 tiles. You can do only 1 or 2 tiles. So design properly to do the experiment. Then save the response of the circuit for all these 5 frequencies and report the same. That's the procedure. Now let us look at one of the differentiator, how actually RC differentiator works for different frequency. In this actually I am going to show only for one particular value, which is 1/10 of the applied frequency. We know that if you use a sine wave, differentiator of sine wave is a cosine wave, and similarly differentiator of a cosine wave is a sine wave. So if you provide sine wave, it's not difficult to identify what would be the output. Instead of a sine wave, if you provide a square wave, what is the output? So that actually one has to think. And for the applied frequency, which is 1/10 of the design frequency, the output looks like something like this. So this is very interesting to understand. See that square wave is already shown in the continuous line, and it is the input signal, and dashed line is the output signal, output of the differentiator circuit. Why the signal is like this? If you analyze this, say from what I will just take the part of the signal here. So for this part, the input is constant, therefore differentiation of the constant is 0. Then the input suddenly decreases to a 0 value from a maximum value. Because of that, you get a peak in the negative side. Okay. Similarly, then after reaching here, the input again remains constant here. Then it suddenly rises to a higher value, and due to this, you get a sudden peak in the output here. So these are actually delta peak. Now for a true differentiator, if the circuit exactly works as a differentiator, these peaks that should be like delta peak. Here the peaks are not delta peak, but they are nearly to the peak. So your actual experiment is to understand the circuit behavior for which applied frequency you get the delta peaks in the output. So that's actually, and for now to understand how circuit behaves, you have to perform it for 5 different times, and you have to understand that. Then RC integrator circuit. That in the RC integrator circuit, we just interchange the locations of capacitor and resistor. This is a low pass filter, and the circuit apart from that almost remains same. So repeat all the steps which are explained in the differentiator circuit, and in this particular case I am going to show only the output for the case of applied frequency matches the design frequency F. So integrator circuit should accumulate all the input signal which are given to the circuit and should provide the maximum output. That's the true integrator circuit. For this frequency, when the applied frequency equals the design frequency, one important output will result. A square wave will be converted into a triangular wave. So this is the characteristic of an integrator circuit. An integrator circuit is one which converts a square wave signal into a triangular wave, but with a loss of lot of intensity or amplitude. So you see that the input is so much, whereas the output is very small. It lies between only these two values. However, that is helpful in converting a square wave signal to a triangular wave signal. But this is not a true integrator circuit. It acts as a converter from square wave to triangular wave. But a true integrator circuit should accumulate all the data which is available in the signal. So your experimental task is to perform this for 5 different trials for 5 different applied frequencies with respect to design, then you have to report the result. Okay, so you have to note down the observations like this, both for differentiator circuit and integrator circuit. For 5 different values of frequencies, you have to note down the input voltage as well as output voltage, and you have to report to the teacher. Okay. Then we move on to the Fourier transform, the second part of the experiment. Fourier transform of sine wave and square wave signal. So square wave you can get from the wave generator with sine wave enabled, that can be connected to any one of terminal. Let it be A1 and connect square wave generator is Q1 to A2. Then after that, you just set the frequency to some value. It can be any value between say 10 Hz to 10 kilohertz. I'm just taken some value about 150 Hz. Then click the FFT button on the monitor. Then that will generate Fourier transform of the two signals, sine wave and the square wave signals. Okay. Then for all these cases, you identify the frequencies and amplitude of all the harmonics. That's actually the task of this Fourier transform study. So Fourier transform of sine wave. What is the Fourier transform of a sine wave? If you do analytically how to get the solution using Fourier transform, you should get two signals on either side of the 0, which is the reference line. If not 0 is the reference line, say W0, then you should get two signals on either side of the W0, negative side as well as the positive side. Negative side usually refers to the phase of the signal and positive side refers to the actual frequency of the input. So if I give certain signal, then sine wave is, if it is monochromatic, pure monochromatic, then it should give only one output, a delta signal like this. So Fourier transform of a sine wave gives a delta signal exactly like this. So if you take the cursor and click at the top of this particular signal like that, then you will get the values of this signal where you click the pointer to be equal to x and y value. X value corresponds to the frequency and y value corresponds to the amplitude. So if you set the frequency as 150 Hz, then x value, frequency value should be around 150 only. So in this diagram, the frequency is shown to be 151. And y value gives the amplitude of the Fourier transform of the sine wave, which gives actually basically the signal strength of the sine wave. Then Fourier transform of the square wave. So if you studied for Fourier series and how to analyze the square wave, you would notice that any square wave can be expressed as a series of sinusoidal waves. That's the actual essence of Fourier series. So if you do perform Fourier transform of sine square wave, you should get many series of sine waves. So that means you should get many delta peaks when you perform Fourier transform of a sine wave like this. So you will get many peaks here like this one, this one, and this one, this one. And they follow the certain pattern, and I am giving you assignment to know how actually the pattern, intensity and frequencies of the signal varies. So that's your actual problem. And in addition to that, you get certain signal here. So that signal is actually exactly at 0 Hz. So that's actually DC component of the square wave. So you get a DC signal as well as AC signal. DC signal because square wave is AC shifted above 0. Therefore, you get a DC signal like that. That's a very important thing you should know that. So finally, you have to report both sine wave frequencies as well as amplitude for square wave. So sine wave we have only single frequency and one amplitude. For square wave we have a DC as well as AC. And in AC contains, the first one contains the input signal, which is the fundamental frequency, and several frequencies which are called first, second, third and fourth harmonics. So your experimental task is to identify the frequency and amplitude of square wave as well as sine wave. So that ends the lecture on experiment of integrator, differentiator and Fourier